definite integral, and then we're going to do the definite integral. So this is just another kind of U-substitution that you can do with what we know so far. So it's just a kind of a special, unique case that we can use what we've learned so far. So remember what we did the other day. I'll set it up for you. But you still let u equal the term that's in the square root. And du is always very easy with these because typically this is just x minus something or x plus something. And then when you take the derivative of x is 1, so you just get dx. So the final thing is this first part you can solve for x. So if you solve the u equation for x, you'll get u plus 4. So then you make these substitutions. For x, you use this substitution, u plus 4. For du, you put in, for dx, you put in du. And for x minus 4, you put in u. And you typically end up, well, you always end up with something raised to a fractional exponent once you multiply it all out. So go ahead and substitute it in, and then simplify, and then multiply out all the terms. So you have two separate terms. You'll have something raised to the half power and something to the 3/2 power. I did notice this. He fixed it the same way I fixed it. He stole the microphone from the other classroom, and I remember when I was messing with it, it had a little bit of noise to it, which I'm hoping will not be too bad. So the first part you do is for x minus 4 you put in u. For x you put in u plus 4. Then this is the simplification part. You're going to convert this to u to the 1/2 power, and then just multiply this by u to the 1/2 and that by u to the 1/2. Okay, so that's what you get. Now what you do is you just integrate normally. So you're going to add 1 to the exponent and divide by the new exponent in both cases. Once you do that, then you'll, instead of dividing by the fraction, you'll multiply by the reciprocal. And then finally, you'll go back and you'll plug in u. So once you've cleaned everything up, you've integrated, you've cleaned it up, Then go ahead and stick x minus 4 back in. So you'll have x minus 4 to the 5 halves times some constant, and x minus 4 to the 3 halves times some constant, plus adding your, don't forget your arbitrary constant. So that's the answer. Anybody have any questions about what we did there? Sometimes people factor out. This is acceptable for me. Sometimes people combine these two terms, so I'll show you how this works. If you factor out or x minus 4 to the 3 halves out of the expression, so if you had x minus 4 to the 3 halves, what that leaves is 2/5 times x minus 4 to the first power. So when you factor out the 3 halves, you're left with 2 halves, which is 1. And then the second term, you're factoring out the entire thing. And then you can simplify what's in here. So you get x minus 4 to the 3 halves times 2/5 x, and then you have minus 8/5 plus 16/5. Is that right? No, 20/5. 20/5 minus 8/5 would be 12/5. So that would be, you might see that sometimes. If you look at it in the book, they may go to this point. But that's fine for me. Okay, so the next one is basically the same thing. The only difference is that you're still going to use u as x plus 2. You'll still solve for x. You'll need to redefine the limits of integration. So instead of substituting back in here, what you'll do is by changing your limits to u, you can just complete it to this point, and then you could use the u limits instead of the x limits. So give that one a try. The next one, which is the integral from 1 to 3 of x squared times the square root of x minus 2. And I forgot the dx, so I put the dx in there. So what is, you got to solve for x. So x is going to be equal to, in terms of u. x equals u minus 2. Okay. So for this you'll use u. Here you'll take this thing and you'll square it. Okay. So when you do the x substitution, you're going to end up with something squared, like a well, not a factor squared. So just square it like you normally do. You'll end up with u squared plus something, u plus something. And then you'll multiply everything out after that. So you're going to have to multiply out the quadratic thing squared, and then multiply it by u to the 1/2 power. So in this case, you'll have 3 terms. So what you're going to have is u to the 1/2 times u squared. So that's going to be u to the 2/2 power, or 5/2, 2.5 power, or 2.5 power, or 5/2. And this one you're going to have u to the 1/2 times u to the first.
So it would be
3/2, and then this one will be just a half. Yeah.
Mm-hmm. Is this supposed to be addition up on the...
Oh. Yes. Yeah, I don't know why I put minus there, so sorry. I'll fix that. du. Okay, so that's, and then multiply that out, and then simplify everything. So what I've done here is for x, I've used this second substitution. For x plus 2, I've used the first substitution. And du is just dx. Then I use FOIL to get that. I change the square root to u to the 1/2 power. Then I multiply this times each term. So you get 4 halves plus 1/2 is 5 halves. 2 halves plus 1/2 is 3 halves. And 0 halves plus 1/2 is 1/2. Make sure you put a parenthesis here. If you just put the du in the end, it's not obvious that the du is applied to everything. I mean, there's probably not another choice, but I would put a parenthesis here. And then when you integrate it, you add 1 to the exponent, divide by the new exponent, add, divide, add, divide. You don't add your arbitrary constant c. So don't ever do this, okay? You probably get the answer right, but you want to, for definite integrals, you never have an arbitrary constant c. Okay. And then we just cleaned up a little bit before we substitute in. So we take the reciprocal of the thing we divide by, and so we'll get the following. So what I'm doing is I'm taking the reciprocal of 5 halves, which is 2/5, and 2 times 4 is 8. So I get 8/5. Same here. Reciprocal of 3 halves is 2/3. 2 times 4 is 8. So you get 8/3. And again, because it's a definite integral, we don't need to substitute u back in. We just change the limits. So you have 2/7 times 5 to the 7 halves minus 8/5 times 5 to the 5 halves plus 8/3 times, and I ended up just doing this as a decimal, so if you're doing it as a fraction, if I tell you to do it as a fraction, make sure you do it as a fraction, but partially because these probably don't necessarily come out to be nice numbers. Okay, and then you subtract the expression evaluated at the lower limit. And if you plug all that in, you get an answer of 17.95. You might want to check to make sure you know how to do those powers. You got to remember, when you do use the calculator, you always have to put the powers in parentheses. So this set to the 7 halves, I would make that parenthesis, left parenthesis 7/2, right parenthesis. Otherwise, it might think it's 5 to the 7th power divided, the whole thing divided by 2. So I'm gonna open up my graphing program here, and I just want to show you the two functions that should have the same area. I always think it's kind of neat that it actually works out that way. So what I'm looking at here is x squared times the square root of x plus 2. Okay. So it's x squared times the square root of x plus 2. And I'm going to go between 1 and 5, because this one goes from 3 to 5, and this one goes from 1 to 3. And I'm going to have to zoom out a little bit here so I can. Okay, so this one goes from 1 to 3, and the second curve is the U-substitution, which is this one. So if I take x minus 2 squared, so x minus 2 squared times the square root of x. So that's the second equation. X minus 2 squared times the square root from 3 to 5. So I graphed that one too. So what that's saying, let me go ahead and grab that and put it on my smart board thing here. So we'll go there, we'll grab the screen. So what we've just shown is that if I find the area under the red curve between 1 and 3, which would be this area here ends up being equal to the integral from 3 to 5 of that one. Actually, they're exactly the same, aren't they? It's kind of funny because you can see if you look at this height here, it's exactly the height of that. The limits are the same in terms of the width of the limits. They're both 2 units wide, and the value of the function is the same at the end of the limit. So this one's, it's obvious they're the same because they are exactly the same area, just shifted by a little bit. Okay, so you guys can turn that in at the end of the period. That was new for this year. So we're going to move on to section 6, which we're just going to finish up today. Then we'll move on to chapter 5 on Monday. So okay, you don't need to write any notes for this. I'm just going to give you a general idea here of what's going on. So, up to this point, we've done what we would call an analytical solution. You remember the other day I was talking about the movie Hidden Figures. I was going to say Hidden Fences, but that was somebody else said that. Hidden Figures. They were doing analytical solutions of the orbits of the spacecraft, and they were trying to merge the analytical solution for an elliptical with an analytical solution for a parabola, and they couldn't figure that out. And so the same thing is true for integrations. We're going to learn some techniques later that allow us to solve quite a different number of solutions, but in reality we might get something like this, which I don't know how to solve, and it looks very complicated. So if I tried to do this, well, actually this one is something that, no, you couldn't, because this is squared. So if you tried to use U-substitution, make that U, and you took the derivative, and if you got 8x squared plus 2, we can't do it. If it was 8x plus 2, we could do the integration, but if it was 8x squared plus 2, we couldn't do the integration. So how do you approximate the area underneath the curve without doing the analytical solution? Well, you use what's called numerical integration. And we've sort of done that when we did the limit definition for finding the area underneath the curve. We use rectangles. And you could evaluate the function at, say, the end of a small interval, this little delta x or dx interval, and use that as the approximation to the area underneath the curve from here to here. But it's not very good because you have this error right there, and even if you make the rectangles a lot of rectangles, you're still going to be still have some error. So the question is, but you could get a pretty good solution if you just made this, instead of 10 rectangles, if you set it up in a computer program so it had 100,000 rectangles. So usually what you do is you're trying to find the most computer efficient way of coming up with an approximation. The brute force way is just to make a lot of rectangles, and you can get there, but there are better ways of doing it. There are better shapes to use underneath the curve to approximate the actual area. So let me so the first better approximation than a rectangle is to use what's called the trapezoid method. And so numerically what you do, instead of just using the value of the function at the beginning of the interval or the value of the function at the end of the interval to define the shape of your rectangle, you would do a trapezoid. So the area of a trapezoid is the value of the function at the beginning of the interval plus the value of the function at the end of the interval divided by 2 times the height of the trapezoid, which is delta x. So that would be an approximation. You can see here that the blue line, which would be the rectangle, versus the red line, which is a trapezoid, the red line approximation is much better than the blue line. You've only got this really little bit of error between the numerical approximation and the curve, because there is some curvature in there. The next level of complexity is what you do is you assume that there's a parabola. You can't do the parabola calculation with just 2 points. You have to have 3 points to make a parabola. So you still increment your x value in constant amounts, but you look at the area under these 3 points, and the 3 points you fit a parabola to it, and that's going to have curvature to it. A trapezoid is not going to have any curvature to it, so you're always going to have some error because of the lack of curvature in your approximation, whereas a parabola does have a curvature. So you can, if you fit a parabola to those 3 points, that parabola is going to closely approximate the black curve. So that's a better approximation. What happens is the equation for calculating the area becomes a little more complicated. So you still have a delta x, but your delta x is actually from here to here, and you take the value of the function at the beginning of the interval plus 4 times the value of the function at the middle of the interval plus 1 times the value of the function at the end of the interval, and then you divide that sum by 6, and that will give you the area under this parabolic approximation to the curve, and that's called Simpson's rule. So there are other more complicated ones. So what you end up doing is your approximation within a small interval is closer to the actual function, but the equation for evaluating becomes more complex, and that's the balance you have with numerical integration type techniques. So I'm just going to demonstrate this. We're going to quickly build those. And what we'll do is so we're going to have n rectangles or n parts, and we'll have the x value. Let's put a little subscript. So x sub I. Where can I do subscripts? Probably there. That's not. There we go. Subscript. Okay, so that's x sub I. And then we'll evaluate the function f of x sub I. Yep, I'm going to go the other direction. Subscripts are annoying, especially in Excel. Undo that. Okay, that's the value of the function at that. And then I'm going to copy this, paste it there so I don't have to fool with the subscript, and I'll just, didn't do my subscript. Yeah, okay. Subscript I. Okay, so that's the value of the function at the end of the interval. So we'll start with 1. We'll do 100. We'll do 100 data rectangles, or whatever we're going to do, okay? Almost 100. Okay. So what we're going to do is we're going to start at x equals 0. We're doing the function y equals x. Well, let's do y equals x cubed plus 1. Okay, that's my function. So this is still going to be just, it's going to be equal to 0 plus n minus 1 times, we're going to be between 0 and 10. So I'm going to take 10 and divide by 100 because I have 100 rectangles. Okay, let's see if this works. The next one should be 0.1 and so forth. If I copy that equation down, okay, so you can see there's the values of x. And I can do the same thing. So now I'm going to evaluate the function. So the function is going to be x cubed plus 1. So that's f of 0. And then I'm going to do here, I'm going to evaluate the function at the next value of x, f of x sub I plus 1. So that's cubed plus 1. So that's the value of the next part. That's the curve's getting larger. Okay, so now I can, what I can do is I can copy those equations all the way down to the bottom. Okay, so if you take 10 cubed, or yeah, so this is 9.9, so f of, or x sub I plus 1 would be 10, and 10 cubed would be 1,000, so I'm not sure why that's not 1,000, but I'll put that in there. 1,000, okay. If you take 9.9 cubed, you'll get 971.222. 9.8 cubed is 942. Okay, so those are just the values of x and the values of the function. If you do a rectangle, what you would do is you would take, so this is we're going to calculate the area of each little sliver of this. So it's going to be 0.1 units wide, and it's going to be whatever the y value is. And I'm going to use the value of the function at the beginning of the interval. So that's going to, so the rectangular area is going to be equal to 0.1, which is the width of the rectangle, because you can see all of these are 0.1, times the value at the beginning of the interval. And if I copy that equation all the way down, and then I add all those numbers together, so I get the total. I get an area of 2,460.25. Okay, we know how to do the analytical solution, so let's just do that. So what I'm looking at here is what is the integral from 0 to 10 of x cubed plus 1 times dx. So I would add 1 to the exponent, divide by the new exponent. The integral of 1 dx is just x. And I'm going to evaluate that between 0 and 10. So then I evaluate it at the upper limit, and I subtract it at the lower limit, which is 0, and then I get my calculator out, wherever the heck I put that, and we'll see what the analytical solution is. So we get 10 to the 4th power divided by 4. Whoops, I did it to the 4th power again. 10 to the 4th, which is 10,000 divided by 4 plus 10. So I get 2,510. So that's my exact solution, 2,510. So if we go back to Excel, my approximate solution was 2,460. Okay, so I'm a little low. And that was using 100 rectangles. Okay, so not bad though, right? I'm close to 2,500. So that's probably my worst approximation. The next thing I'm going to do is a trapezoid. So we'll put that in trapezoid. So the way you do a trapezoid is the area under the trapezoid is equal to the value of the function at the beginning of the interval plus the value of the function at the end of the interval divided by 2 times the width of the rectangle. So I'm averaging that was my formula, remember here, for a trapezoid, you take the value of the function at the end of the interval plus the value of the function at the beginning interval divided by 2 times the difference. So that is what I get. And if I copy that area all the way down, so I'm calculating this for 100 trapezoids, and then I copy the equation, I get 2,510.2. Okay, so that compares with the exact solution of 2,510. Obviously, the trapezoid solution, using trapezoid method instead of the rectangle method, you get a heck of an improvement in your solution. We're still off by 2/10, okay? It's not very much. And the reason is because x cubed is reasonably linear, so the trapezoid way works. Now, this is the next one. This is the hard one. Using Simpson's rule, and the way it works is you go to the middle of the interval, and you take, let me remember how this goes. You take the width of 2 times, so it's instead of 0.1, it's 0.2. You divide by 6, and then you multiply by the value of the function there, plus 4 times the value of the function here, plus 1 times the value of the function there, and that gives me an area. So what I have to do is I have to copy that equation every other slot here, because so that's going to take me a while, except what I'm going to do is I'm going to then do this, and then I'm going to copy it like that, and then if you take that, then you double it, and then we do it again, and ultimately we get to the end pretty quickly as far as copying the equation. It's just a way of, since it's every other one, it becomes a little more complicated, but you can see it's happening. And one more, and then I can delete the extra stuff that I have in here. So delete all this junk. Delete. So now if I add all those together, again, let me just copy the formula. And that's worse. So what did I do wrong? This number apparently is not going to work because it's I have to go one more step here. Okay. So I'm going to copy this down to there. No, that's not going to work. Okay, so I'm just going to enter 10. And then this goes there. There you go. Okay, I had to go one more step because of the 3 spots. And you can see the Simpson's method comes up with the area as being 2,510. Okay? So the point here is that to do a complicated integral that there's no analytical solution to, you can approximate the area under the curve in the simplest case by using a rectangle. The next one is the trapezoid, which makes a huge improvement. I'm within 2/10 out of 2,510. If you're designing something, that's close enough for government, that's better than you can expect. Then if you want really accurate stuff, instead of doing a trapezoid, you fit a parabola, sorry, spit there, a parabola to the function using the 3 points, and you get an even better solution. So that's how numerical stuff works. And if you go online and you do one of these numericals, if you go, sometimes they'll work out the analytical solution, but they'll give you the answer, and a lot of times the answer is done numerically. It's not done analytically. There's one other, let me see if I can, yeah. Most likely they're using Simpson's rule if they're doing it numerically, because you can see unless the curvature of the function is really high, you can get a pretty good approximation using Simpson's method. So that is it for section 6. I'm not even going to assign any homework for that. I might have some on the end, but I'm going to, yeah, we're not going to, oh, that's more chapter 4 homework, which I think I've already, section 5, so I won't assign that. I think I've already assigned that anyway, so. So no homework out of section 6. Okay, so now we're going to move on to chapter 5. I have posted the review for test number 4, so if anybody wants to study early for it, they can. It's mostly section 5 stuff, because section 5 stuff uses section 4 stuff and section 1 stuff. The only difference, I think there is one problem that would be out of section 1, which is where you solve a differential equation, where you take y prime and you make it into dy dx and multiply both sides by dx. Otherwise, it's just doing a lot of section 5 problems, all the different U-substitutions that we've played around with. So. Okay, chapter 5. So chapter 5 is going to talk about logarithms, exponential functions, inverse sine and inverse cosine, and inverse tangent. So those are the main things. So we're going to have to, one of the special cases that we haven't handled yet is what is the integral of 1 over x dx. Because that's when x equals -1, and that the formula, the integral of x to the n dx, which is x to the n plus 1 over n plus 1 plus c, does not apply. Okay, so this is x does not equal -1. So we got to figure out how to handle that. And since the exponential function is a inverse function of the logarithm, which we'll find out the actual solution to this is the natural log. But we can use that information from this section to find out what the integral of e to the x is. And then, we have the inverse trig functions that we haven't dealt with. After we get through chapter 5, we'll pretty much have all of the integral formulas. If you look at that handout I gave you that has the trig identities on one side and the integrals on the other, you'll notice that if you look at the bottom, it's the inverse trig functions. So we'll have all of that table filled out. We'll spend most of the second semester using that information in other ways to get the answers that we need. Okay, so this is I came up with this explanation, so hopefully. So the question is, what is the integral of 1 over x dx? If I hadn't told you it was the natural log of x. Well, you might think, well, you mean I can do 1 over x to the 0.999 power, and I can use the formula, and I can use 1 over x to the 1.0001 power, and I can get the curve, but I can't get 1 over x to the first power. So it seemed like, so I had this idea. Let's say we wanted to find the area, or the area underneath the curve x squared dx, or just x squared. And let's say I couldn't evaluate, for some reason I couldn't use the formula at x equals, or n equals 2, where you have the exponent 2. Well, if I were to find the area underneath the curve x to the 1.9 power, which is the blue curve, and then I found the area under the green curve, which is x to the 2.1 power, and then average that area, you would expect that to give you the area under the red curve, which is x to the 2 power. So that seems like a reasonable assumption, right? That if I do that, I'll get approximately the right answer. This is going to be a little bit more than the right answer. This is going to be a little bit less than the right answer. So I just average those together, and I should get pretty much the right answer. Okay. And you can prove that by doing this. So if you take the integral from, say, 0 to 3 of x squared dx, so analytically we add 1 to the exponent, divide by the new exponent, evaluate it at the upper limit, so you'll get 3 cubed, which is 27, minus divided by 3 is 9, and then you subtract the lower limit, which is 0. So the area underneath that curve is 9. If I do the same thing for the function x to the 1.9 power from 0 to 3, it should be less than 9. And, I add 1 to the exponent. So 1.9 becomes 2.9. I divide it by 2.9. I go from x equals 0 to 3. I get 8.34, which is less than 9, which is what I expected. And I do the same thing then for 2.1. I add 1 to the exponent, divide by the new exponent, evaluated the upper and lower limits, subtract the lower from the upper, I get 9.72. If you average those two areas together, you get 9.03, which is approximately equal to 9. So it works, okay? I didn't need to do this to probably prove that it actually works, because you can just look at the picture and say, yeah, that makes sense. So I said then to myself, what if well, before we do that, let's plot the function that we don't know the integral to. So the function we don't know the integral to is 1 over x. And there it is. It's just a reciprocal function, has a vertical asymptote at x equals 0. And if you look at the curve, there's area under there. Okay, so there has to be an answer. There has to be some number. Therefore, the integral of, say, 1 over x dx from 2 to 3 exists, because I can see it. It's not like it doesn't exist. There's nothing special about that function that make me think that it doesn't exist. So knowing that it has to have a number, that's when I use this approach. So what I can do is, remember, this formula works except when n equals -1, it doesn't work. So what I'm going to do, I'm going to use the formula, but I'm going to use it very close to the actual value where it doesn't work and see what happens. So if I have n to the -0.9 power, that's the same as 1 over x to the 0.9 power. That's pretty close to 1. If I do it on the other side, n is -1.1, that's on the other side of 1. So it's -1.1 here, it's +1.1 there. So when I integrate it, I add 1 to the exponent. So that's n plus 1. And if I use that example and I add 1, I get -0.1. So then if I do the integration, and I'm not doing it between any two numbers, I'm just looking at it generally. So the integral of -0.9 dx is x to the 0.1 divided by 0.1. So I add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent, which is -0.1. And then I plot those functions to see what they look like. So if I plot this function, x to the 0.1 power divided by 0.1, it looks like that. Okay, that's this function. If I plot the second function, which is negative x to the -0.1 divided by 0.1, it looks like that. So if I add those two functions together and see what it looks like, then that should give me an idea of what the actual solution to the one that's in between. What does the function look like that's the integral of 1 over x dx? So you can put those two together. If you graphically add those two together, what you end up with is this. Okay, so you take this function and add it to that function, and it looks like that. Okay, and the question is, what does that function look like? Well, it's a function that has a vertical asymptote at x equals 0. The value of the function, adding those two together, the value of the function is at x equals 1 is 0. And the value of the function at 2.7128 is equal to 1. Well, you would say, well, I know a function like that. That's the natural logarithm function. So that's my way of coming up with kind of reasoning through why the integral of 1 over x dx is the natural log. I kind of broke it down into two parts. Approximate what the function, the integral looks like, the function, the integral that represents the function, by looking on either side and averaging them. And if you average these two functions together, you get something that looks familiar, which is the natural log function. So that's one way of doing it, okay? The other way of doing it is the way the book does it. Is they look at the area underneath the curve from x equals 1 to some value of x. And they say, hey, I'm going to define that area as the natural log of x. So it's like you never took pre-calculus. So in pre-calculus, what they did is they introduced the exponential function. So x to the not x to the n, and it was 2 to the n power, 3 to the n power. In case of the natural log, it was 2.71828 to the n power. And then the natural log was the inverse of that function. So we define the logarithm as the inverse. The natural logarithm function is the inverse of the e to the x power. In calculus, what they do is they define the natural log function as the area underneath the curve from x equals 1 to some value of x of the curve 1 over t dt. So it's kind of a different way of thinking about it. And then what you do is using this definition, then you define the natural exponential function. But, I mean, ultimately, you don't have to worry about the details of how this all comes about. It's kind of a subtle thing. So again, it's kind of like when we did the indefinite integral and we put the integral sign, you're like, why did we use that sign and why did we put dx there? Well, because ultimately we're going to use the same symbolism, the same terminology to talk about taking the antiderivative and evaluating it as a definite integral. Here it's kind of the same thing. We end up calling it the natural log because we know later on that it's the same thing as the natural log that we defined in pre-calculus. Okay. The bottom line is this, okay? We have a new formula, and the formula is that if for the special case of x to the n, where n is equal to -1, and that doesn't work, we have this one special case. So the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So that just gives us one more formula. The other interesting thing is, for the other integrals, we figured out the integrals because we knew what the derivatives were. We said the derivative of the sine was the cosine, therefore the integral of the cosine is the sine. The derivative of the cosine is negative the sine, so the integral of the sine is negative the cosine. So we used the derivative to figure out what the integral was. In calculus, the natural logarithm function is the only one that's done the opposite way. We define the natural log function using the integral first, And then because the integral and the derivative are opposites of each other, then we can say if the integral of 1 over x dx is a natural logarithm, then the derivative of the natural logarithm is 1 over x. So that's a unique thing. Now notice there's two cases here. The derivative of the natural log of x is 1 over x, and the derivative of the natural log of the absolute value of x is also 1 over x. Okay. So even though this is derived, and it turns out we have to use an absolute value, which I'll explain Monday. Here it doesn't matter whether it has absolute value or not. Okay, we'll continue on Monday on that one.